Good afternoon. This is our video lesson. Sorry, not a video lesson. This is our narrated PowerPoint for sedimentary rocks and weathering. I will be filming video lessons on this beginning next week. So our opening slide here, we are looking at an image of, you guessed it, the Grand Canyon. So the coolest thing about the Grand Canyon is that 1.7 billion years of geologic history is exposed at the Grand Canyon. From the Vishnu schist all the way at the bottom where the Colorado River is, all the way up to the Kaibab limestone on top. Okay, so I might want you to know a definition of sediments and what might be included in sediments. So sediments are unconsolidated or loose fragments of minerals and rocks. Where do they come from? They come from bedrock. So unconsolidated loose fragments of minerals and rocks that have weathered out of bedrock. It also includes mineral crystals that precipitate out of water. That could be a surface water solution or a groundwater solution. Minerals such as calcite, halite, quartz. It also includes seashells. So what kind of things are included as sediments? Sand, silt, clay. That's kind of going in an order of size from largest to smallest. It also includes mud, which is basically silt and clay with water. Shells, shell fragments, mineral and rock pieces, gravel, evaporite minerals such as halite and gypsum. So what we're looking at here are some images of sediments, and if we have time to show this in class, I'm going to point to the image here on the left. I'm going to ask you guys, can you tell me where this image is taken? Okay, so if you guessed it's in the mountains, that's correct. It's a mountain stream. Now then the next question is, what size sediments do you see here in the mountain stream? I mean, does it look like a bunch of small beach sand, or does it look like larger pieces? Do we have anything for scale? Yes, we have trees. Okay, so these are larger pieces, boulders, cobbles, pebbles, and perhaps some sand. So just some images here of sediments. In the top left, clearly that's a bunch of sand. That's on a beach. In the top left corner, you might see a little slice of water there. Bottom right, we're looking at gravel-sized pieces. Everybody knows what gravel looks like in a driveway or parking lot. By the way, in North Carolina, I guess it depends on what part of North Carolina you're in, but common rock types used for gravel would be granite. And more towards the coastal area, it might be limestone. It depends on what kind of rock you have nearby, because rock is heavy and therefore kind of expensive to transport. And then in the bottom left image there, in general, what size sediments do we think are mixed up in that pretty stagnant looking water there? You guessed it, smaller sand, or smaller grain sizes. Perhaps some fine sand, definitely some silt, definitely clay in that water. So smaller sediments indeed. Grain sizes, I'm going to want you to know the relative grain sizes. You do not need to know their size in millimeters, just kind of know them from the largest down to the smallest. Okay, so we'll begin with the largest. Boulders. Boulders are very big. They are greater than 256 millimeters or 25.6 centimeters. Boulders have no upper limit. Okay, so some boulders could be, well, as large as a two-story house. Then we have cobbles, 64 millimeters, going all the way up to 256 millimeters. Cobbles are pretty big, so perhaps something like the size of a basketball or a grapefruit or a softball. Pebbles are anywhere from 2 millimeters up to 64 millimeters, smaller than cobbles. Sand. So the geologist is going to break sand down into about 12 different sizes. We are going to keep it simple and just say that sand can be as large as 2 millimeters to as small as 1/16 of a millimeter. Silt is smaller than sand, but not the smallest particle. So silt, the medium to larger grained silt, those are particles that you can still see with the naked eye. Clay. Okay, so clay sized grains you are never going to see with the naked eye. Why? Imagine 1 millimeter. Like hold your thumb and forefinger together to show 1 millimeter. Now imagine dividing that up into 256 equal parts, and the size of clay is less than one of those parts. So clay minerals, for example, can only be imaged with a scanning electron microscope. I think you guys saw an image of that on one of the slides in the mineral lecture. Sedimentary rocks. You're going to need to know both of these bullets here for your second exam. Sedimentary rocks, how do they form? They form when sediments are compressed or squeezed together, but also cemented together, as in some kind of mineral that acts as a glue, a natural cement. Where do sedimentary rocks form? You need to know that. That's very important. That's why it's in bold print and italics. Sedimentary rocks form only in the upper portion of the crust. Why? Because they're only going to form where weathering is occurring. Weathering is occurring, of course, at Earth's surface and in the upper portion of the crust. Now, generally, our sedimentary rocks are going to cover older igneous and metamorphic rock, what we might think of as bedrock or perhaps even basement rock. All right, for your second exam, I'm going to want you to know the difference between bedrock and basement rock. So we'll begin with bedrock. Bedrock is basically any hard rock. Okay, so often it's in the subsurface. We expect bedrock to be covered by sediments, soil, but sometimes bedrock is actually sticking up out of the ground. So where bedrock is exposed at the surface, we refer to that as an outcrop or a rock outcrop. So any hard rock is considered bedrock, be it in the subsurface or at an outcrop. Now, in most places, the bedrock is covered by sediments, but not in all places. So look at these images. Well, the image here in the bottom right, you're looking at some core sample. So core sample, what does that mean? It means that we drill into the subsurface and we bring up samples of rock, sediments, and perhaps soil to study. So what you're looking at here, this is actually a relatively local example. This is the Castle Hayne limestone. So this is down there kind of in the Wilmington area. I do know that they were drilling into this particular limestone near Elizabethtown, so basically coastal plain. And of course, this was indeed part of the USGS Coastal Plain Drilling Project. Limestones, most are fossiliferous. This one is. Basement rock. Okay, so any hard rock could be considered to be bedrock. And basement rock is hard rock, so basement rock is a type of bedrock, but not any bedrock is going to be basement rock. So what makes the difference? Basement rock is much older. Okay, millions to billions of years in age, usually tens or hundreds of millions of years to billions of years in age. Basement rock is also either going to be igneous or metamorphic rock. Okay, so sedimentary rock is never considered basement rock, and basement rock is making up the lower portion of the crust. Some examples of common rock types that make basement rock would include granite, which is an igneous rock we learned about in our second unit, and then a couple of metamorphic rocks here that we haven't learned about yet, gneiss and schist. That image on the left is very likely coming from one of the Great Lakes. So you are probably looking here at the Canadian Shield, which is somewhere where you have a lot of very old basement rock exposed at the surface. And notice the bands of color in that rock beneath that person's feet. So that is something referred to as banded gneiss, and that is a type of metamorphic rock. The sample on the right is known as mica schist. The natural cements, you're going to need to know these 4 natural cements for your second exam. So natural cements are minerals that grow out of some kind of water solution and effectively glue the sediments together. Okay, so they include quartz, which is a common cement, and it's a very strong cement. Calcite, which is a weak cement. Remember calcite? It's the dominant component in the medicine Tums. So calcite can make a natural cement, but it's very weak. Mud, which is again basically silt and clay and water mixed together. Mud can make a natural cement, but it's a relatively weak cement. And then iron oxides such as hematite. In a normal on-campus semester, we would have passed the hematite around for everybody to look at, and everybody would have run the hematite across the streak plate and see that it gives you a red streak. Okay, so hematite is a common iron oxide mineral, and hematite actually makes a very strong cement. Now, the portion of this unit that we do in class, I will hold up a sample for you guys to look at that is an iron cemented conglomerate, and I used to like to pass it around in class, but that's not going to happen. Not in COVID, not during an alternate hybrid class or an online class. Okay, very important slide here. Why are sedimentary rocks important? 4 reasons. This is a short answer question on your second exam. Okay, short answer question, not multiple choice. Why are sedimentary rocks so important? Well, number 1, they are the source of most of our natural resources. Most of them, not all of them, but most. At least the old school natural resources, our fossil fuels, for example. Okay, second, sedimentary rocks hold most of Earth's history. Well, certainly all of life history is held in sedimentary rocks. Most history about how climate and conditions have changed is held in our sedimentary rocks. Now, the oldest rocks on the planet do tell us a little something about how old the planet is, tell us a little something about the rock cycle. The oldest rocks are not sedimentary, but all sedimentary rocks tell us something about Earth's history. Number 3, sediments are important because of soils. So where are sediments coming from? They are largely coming from sedimentary rocks. And so to be fair, sediments that come from igneous rocks or metamorphic rocks can also help produce good soils. And for example, our igneous rock, particularly the extrusive variety, the volcanic rock, makes good fertile soil. But a lot of the source of our soils is coming from sediments that eroded from sedimentary rocks. And last bullet there, sedimentary rocks store and transmit groundwater, meaning that they make a very good aquifer. Okay, so the image on the right is, of course, an oil gusher. That image looks to be pretty old, probably several decades old. The image on the left is a lot of fun. This is Zephactinus. This is my favorite bony fish from the Cretaceous. Okay, so look at that thing. I know we have nothing for scale there. That's just how it is. That's an image from a museum. But look at those scary teeth on Zephactinus. After watching Shark Week and Shark Fest was basically all summer long on the Nat Geo channel. I don't know if I'll get in the ocean ever again, but I'm really glad that Zephactinus is not still out there. Okay, so this is an awesome image, and this is one that I do plan to show in class for our discussion purposes. But, we're going to go ahead and discuss it here anyway, because some of you, this is all you're going to see. And this will also help my summer online classes. So what we're looking at here is the San Joaquin Valley in California. Okay, so this is part of the Central Valley where you have a lot of agriculture. You certainly see some agriculture things growing there to the right. So you've got a telephone pole. You have placards on there with numbers, 1977, 1955, 1925. Yes, those are years. And you see a man standing there. He's probably at least 5.5 feet tall. Okay, so what do those placards indicate? I'll give you a second to think about that. Those are important markers. They're there for a reason. Okay, if any of you guessed that's where the land surface was back then, you're correct. Okay, so this photo in 1977, that's where the land surface is. But you see they're way up above the guy's head. That's where the land surface was in 1955. And then much further up is where the land surface was in 1925. So in class, I like to ask, what happened here? And I get all kinds of hypotheses. Maybe just weathering and erosion took everything away. Maybe there was an earthquake and caused settling. Maybe there was some kind of, I don't know, tsunami flood that wiped everything away. Okay, well, if you guessed too much groundwater withdrawal, you would be correct. So what the farmers did here in the first few decades of farming this part of California is they drew way too much groundwater out of the ground. And so basically the aquifer collapses and the ground sinks. We refer to that as subsidence. So this is bad. Okay, so not only is your aquifer, you know, nearly depleted, but the aquifer's now been damaged. It'll never have quite as high numbers on porosity and permeability as it had before. Okay, weathering. You're going to need to know about weathering. I do hope to have time in class to discuss at least the types of physical weathering because they are the most fun. So first of all, what is weathering? Well, it's the process by which solid rock gets broken down into sediments. Solid rock, bedrock, gets transformed into sediments. So this is going to happen either by physical means, such as breaking, or by chemical means, which can include corrosion. So we will go into more detail on the types of physical weathering and the types of chemical weathering. Okay, physical weathering. A definition of physical weathering before we get into the types. Well, it's of course referring to physical breakage of minerals and rocks. So there are no chemical reactions involved, there's no corrosion, there's no dissolution, nothing is turning into a clay mineral here, just mineral and rock fragments breaking into smaller and smaller pieces. That is physical weathering. How about chemical weathering? So in chemical weathering, of course, you're going to have chemical reactions. Otherwise, you wouldn't be having this chemical weathering. So what are these reactions going to do? Well, they can alter or change minerals. They can destroy minerals, or they could corrode minerals in a rock. Corrosion, of course, makes you think of rust. So yes, we're talking about oxidation. And this chemical weathering, these chemical reactions are going to occur when the rock is exposed to water and or air. You don't even need water, it just takes air. Okay, types of physical weathering. You're going to need to know all the types of physical weathering for your second exam. This is going to spill over onto other slides. If you do make it to the in-class portion for this chapter, we're going to have drawings of these on the board, and those drawings are very helpful. Okay, so first we're going to begin with jointing, or the formation of joints. Okay, what are joints? They are natural fractures, cracks, openings that form as a rock is exposed to the surface through erosion and then cools slightly, but more importantly, confining pressure is released. Okay, so in parentheses there we have unloading. That's because some textbooks refer to this as unloading. I learned it as jointing years ago, and that's what we're going to go with. So, how do these natural fractures form? So imagine that you have a sandstone that is buried to some shallow depth, covered by sediments. So it is under some amount of pressure. Well, erosion over time takes away the sediments on top, and now that sandstone is exposed at the surface. It's sticking up out of the ground. It is an outcrop. So that confining pressure has been released. So the volume of the rock is going to change. It's going to expand ever so slightly, and that is enough to cause fractures, cracks to occur in the rock. Okay, so we're going to jump around a little bit as we would in class, I think. No, we're not going to jump around since you don't have the drawings right here. So we will go to exfoliation next. Okay, so exfoliation, this is something that in particular is occurring to granite and perhaps diorite. So granite, a common intrusive felsic igneous rock. So what happens here is that when you have a granite pluton exposed at the surface, it's going to be subjected to exfoliation. Some textbooks refer to this as sheeting. So granite splits along joints that are parallel to the mountain face. So what are joints? Joints are those fractures or cracks that form in this rock after it is exposed to the surface. And that will initially happen just because pressure, confining pressure, is released. So in class, I'm going to have a drawing for you and show you what we mean by joints that are parallel to the mountain face. The mountain face is, of course, the part of that rock that is facing you. So exfoliation is happening to granite all over the world right now as we speak, tends to form a rounded surface. Okay, frost wedging. Let's imagine that sandstone again from our first example there. The sandstone that was exposed at the surface and then formed a bunch of cracks or fractures, joints. So let's say that this is in a state a little further north of us, and it's November. It's up in Maryland. It's November, and in the daytime the temperature is 40 degrees, and it's raining pretty heavily. Is rainwater going to get down into the fractures of that rock? And the answer is yes, very easily so. Overnight, that temperature is going to drop down to 30 degrees. What's going to happen to the water in those fractures? It's going to freeze. Okay, so the volume of H2O is going to expand when it's in the frozen form. Okay, so the water freezing into ice in the fractures is going to expand. So every time this happens, it's going to widen that fracture a little tiny bit. Abrasion is simply breakdown by material transport, just saying that you start with a rock outcrop up in the mountains and you get pieces that weather and erode out, and now they're being carried downhill in streams, and as that material is moving downhill in the stream, it's going to be hitting other particles of rock or bouncing off a bedrock in the bottom of the stream, and further breakdown can occur. Moving on, root wedging is exactly what it sounds like. You start with those joints, fractures. Can you have soil form in those fractures? Absolutely. Can you have bushes and trees growing into those fractures? Yes. Okay, so as these bushes or trees grow larger, as they're growing out of that rock, the roots and even the trunk of that tree will, with time, make that fracture wider. Then we have salt wedging, which is just what it sounds like. Salt crystals, halite crystals, precipitating out of groundwater into the fractures and widening the fractures with time. Thermal expansion, of course, has to do with forest fires. There are many blazing in California right now, unfortunately. So heat from forest fires causes the outer layer of rock to expand, and then when the fire is finally put out or just extinguishes itself, that rock's going to cool again, and then it will contract. So you have changed the volume of the outer layer of that rock. Is that going to cause breakage? Absolutely. Biological activity is mainly referring to burrowing creatures in the subsurface. As they are burrowing and making their homes and tunnels, they are breaking rock in the sediment there down into smaller and smaller pieces. Are humans included in biological activity? Well, of course we are. And in class, I'm going to ask, can you give me some examples? So things you're going to come up with would be mining, rock quarries, blasting into a mountain to build a tunnel, blasting into the side of the hill to put in a road. Yes, humans inflict biological activity, physical weathering on rocks all the time. How about some images here? Okay, and that image there on the top left, that's a road cut. You see the road there, cutting through the mountain. And you're going to notice some lines. Okay, so you see many horizontal lines, and a lot of those horizontal lines are actually bedding planes. We'll talk about bedding planes soon enough. This is going to be a really long PowerPoint, by the way. But you'll notice at least 3, maybe 4 lines going vertical up and down. Those are definitely joints or fractures. The image over there on the right, we have joints, fractures in the horizontal and vertical dimension. And you notice that one there that's vertical, and that rock has now been basically completely separated away from the bedrock. So this is an experiment you could perform at home if you want to. I might recommend putting some plastic down so that you can easily clean up the broken glass out of your freezer, but this will work. So if you take a clear plastic bottle and you fill it all the way to the top with water, and then you put the lid on tight, and then you put it in the freezer, what's going to happen is that ice is indeed going to expand and it has nowhere to go, so it's going to break the glass. If ice is strong enough to break glass, is it strong enough to break rock? And the answer is yes. So here's a step-by-step version that would take quite a long time to go from what you see on the left to what you see on the right. So you have one of these joints, fractures, and especially if you're in an area where you can get some low overnight temperatures, you're going to have lots of these freeze-frost cycles, frost wedging cycles, and eventually it can cut a block completely off of the rock. Here's another example of frost wedging. So the image you see in the background, clearly that's up in the mountains, and it looks like up above that lake, you're actually above the tree line. So this is a pretty high altitude. You see all of that rock in the background. You do see some layers in that rock, bedding. Notice all that material that's coming down the slopes. We refer to that as a talus slope. Okay, so that's basically rock debris that has eroded out of the bedrock there, and it hasn't moved very far away yet. And the inset up in that top left is just showing how frost wedging can indeed not only break a piece of rock completely off of the bedrock, but kind of chuck it out onto its side. So, exfoliation of igneous rocks. I really like to show this image in class, and we're going to, assuming we can still have in class for a while to come. Maybe we will all semester. Who knows what's going to happen? But anyway, all right, so over on the left in the drawing, you have a granite pluton. Once upon a time was buried in the subsurface and was under confining pressure. Okay, and then in time two, a lot of material on top weathered and eroded away, and you now have a good portion of that granite pluton exposed at the surface. So you're going to start to get joints to form, fractures. And again, exfoliation occurs where you have rock splitting along these joints that are parallel to the rock face. So I want you to now look at the image on the right, which is the summit of Half Dome. This again is in Yosemite National Park. Okay, so look at the top right portion of that rock. Do you see how choppy that looks? Okay, and you see those layers that are just getting ready to fall out of there. Now, my next question for you, and I'll ask this in class. Do you see the people on the rock? And at first you might say, what people? I want you to look over on the left of the rock. There is a ladder, basically, that is attached to Half Dome, and you can climb your way up to Half Dome. And I'm glad they put it over there on the left, because that looks to be a safer place than if they put it over there on the right. I'm sure you probably have to sign a waiver before you get on that rock saying that if you get killed, that your family members cannot sue them, because you are understanding the risks before you do it. I'm not sure whether or not I would climb that ladder. So other examples here of exfoliation. These are also examples of granite plutons. Okay, so on the left is Stone Mountain, Georgia. That's a neat place. I guess it's a state park, I'm assuming. It's down there near Atlanta. That is an exposed granite pluton, and it is indeed quite rounded, but it becomes more rounded after exfoliation takes place. Okay, so the image on the right That is, of course, from Yosemite National Park, and that is Half Dome, which is a very famous granite pluton in Yosemite. And you'll notice that it is half a dome. Okay, so what made it half a dome? I'm going to have to pause for a second and move some cat food out of the way. No, you will not get any more food right now. Okay, pardon the interruption, but one of my cats is super overweight, so she can't just have food sitting out all day long, and I have food out for the other cat, but the chippy cat was coming over to try and get the food. I had to take it away. All right, back to Half Dome. So, in class, I like to ask, what do you think went through this valley and took away half of that dome? So you think about it for a few seconds. You know, some of the hypotheses that I have heard in the past are, could it have been an earthquake and it split along a joint? Sure, that's a great hypothesis. Could it just be typical weathering and erosion? Maybe, but I'm looking for specifics here. And eventually somebody will come up with, how about a glacier? And that is the correct answer. So glacial activity took what had been an entire dome and carved it into half dome. Okay, take a look at this image here. This is one of my favorite images of physical weathering. Can you guess what kind this is? Yep, this is root wedging. So here it's not just the roots, but part of that tree trunk is growing out of that fracture. And then you'll notice there that the fracture, it's getting skinnier as you move down to the, say, lower right. But what's eventually going to happen to that piece of rock and the tree? Yep, you guessed it. They're both just going to fall out of the rock. So that's root wedging. Here's another cool example of root wedging. This, of course, is urban root wedging. So this is an older neighborhood, and that house has been there for a while, and that tree's been there for a while. The tree was a lot smaller when it was planted there, and the sidewalk was put around it, or maybe the tree planted. The tree could have been there natural, and they just left it, but they put the sidewalk around there, and as the tree grew bigger and the roots grew bigger, they have busted up the sidewalk. Talus. This is a new term I'm going to want you to know for your second exam. Physical weathering may produce talus. So what is talus? It is simply rock debris that accumulates at the base of a slope. So the image there on the right is basically the same image we looked at earlier when we were, one of the times we were talking about the frost wedging. And you see the talus slopes there. I like the one on the left though, because we have a person for scale. And that person is attempting to walk on that very steep slope. Do you think it's going to be easy to walk on? No, gosh no. Okay, it's steep. There's a bunch of unconsolidated material. Every step you take, you have to be careful because things could just slide out from under your feet. It's not easy to walk on a talus slope, but it is really cool. Okay, so this was one of my favorite national parks out west. Back in 2012, we did a Maymester trip out west, and we flew to Vegas and rented vans, and then we went around to a handful of the national parks. Can you guess which national park this is? Of course you can. This is Arches National Park. This is the most famous arch. It's the most photographed arch. It's called Delicate Arch. You won't see this from the road. And if, like me, you have a handicapped family member, you're not just going to get that family member to Delicate Arch. You have to hike, I think it's at least a couple miles. It's easy hiking, and it's worth hiking to get out there and look at Delicate Arch. But so what I'm going to ask you guys is this. First of all, are these arches going to stand forever? Well, of course not. We have weathering and erosion on this planet. We also do have earthquakes. So can you tell why it's called Delicate Arch? Can you find the place where it's most likely to fail first? Let's see, can we move the cursor works right there. That's where it is most likely to fail first. Over there on the left in the middle where it's kind of skinny. Okay, so chemical weathering So physical weathering is a lot of fun. Chemical weathering is important. It may not be quite as much fun, and in class we won't have any drawings for physical weathering. I'm sorry, we will have drawings for physical weathering. We won't have any drawings for chemical weathering. So how does chemical weathering work? Well, it can alter the internal structures of minerals by either removing some elements and or adding some elements. The most important agent is water, but even if water is not present, you can still have chemical weathering. So what kind of things happen? Well, oxygen dissolved in water can oxidize minerals. Carbon dioxide dissolved in water can form carbonic acid and change the minerals, including changing some of our silicates like feldspars into clay minerals. What else can happen? Even in the absence of water, you just need air, and there's 21% O2 in the air. So oxygen in the air oxidizes any minerals there that are rich in iron and or magnesium. All right. So dissolution, you're going to need to know that one for your second exam, is exactly what it sounds like. Minerals dissolving in water. So that water, groundwater or surface water, is probably going to be slightly acidic, meaning that you have formed some carbonic acid. So if the water is slightly acidic, then this dissolution will happen even faster. Okay, so some examples of minerals that will dissolve in a water solution are halite, NaCl, calcite in the Tums, and quartz. Quartz takes a long time to dissolve, but it can happen. So what does dissolution do? Well, it can take those joints that already exist and make them wider. It also can form caves, both in limestone but also in sandstone. Okay, now hydrolysis, as you're taking notes here, I would say that you can just write down the first part of that sentence. When you get to the parentheses, there you could stop. So hydrolysis is the process by which some silicate minerals, like perhaps some of the micas and feldspars, will break down into clay minerals. You do not need to know what's in parentheses, but we will discuss it. So if that water is slightly acidic, like a carbonic acid, then this hydrolysis will happen even faster. So what happens is you take your H2O and you split it up into hydrogen cations and hydroxide anions, and those go in and replace some of the elements in the crystal lattice. So this can help to break down compounds, but also might completely change the chemical composition, giving you a completely different mineral. Oxidation. This is exactly what it sounds like. Basically rust, we might say. So this is a chemical reaction in which an element or compound is going to lose electrons. This is important in decomposing minerals that are rich in iron and or magnesium. Hydration, I'm not convinced it's technically weathering, but every textbook considers it weathering, and it's always put into chemical weathering. So it's the absorption of water into the crystal lattice, and it generally does not change the chemical composition. So that might almost be better served under physical weathering. And it doesn't matter for your exam because I'm not going to ask you to know hydration for your second exam. An example of hydration would be opals. Opals are a type of gemstone, and opals are made of microcrystalline quartz. But opals are pretty easily scratched, while amethyst, purple quartz, is not. What makes the difference there is that opal is hydrated. You have water in the crystal lattice. So the opals are, well, they're not very strong gemstones, although they are pretty. An example of oxidation, you don't need to know this for your exam, but you can start with iron, say from basalt on the Big Island of Hawaii, combined with oxygen from the air, and form the mineral hematite, which has a reddish-brown color. Sometimes it has a silver color, but will still show up reddish-brown when you color it on the streak plate. Example of a natural acid. I'm not going to ask you to know this for your exam. So water, rainwater, picking up carbon dioxide in the atmosphere as it falls down to the surface, can form H2CO3, which is weak carbonic acid, and one of the carbonate anions. So this carbonic acid will easily help to dissolve some minerals. Okay, chemical weathering of granite. I think what we're going to do here is we are going to skip this slide and we'll pick up on this on an upcoming slide. Although that middle bullet there is true. So quartz, I think we talked about this when we talked about Bowen's reaction series. Remember that quartz is the last mineral to crystallize out of the melt at the lowest temperature. It's therefore stable at low temperatures like at Earth's surface. So quartz, while we might physically weather it all day long and break it into smaller and smaller pieces, quartz is not going to chemically weather. Why not? Well, it doesn't have iron and magnesium. To follow up on that last slide, not only does quartz not have iron and magnesium, it has no metal at all. If it had any metals in it at all, it would be subjected to chemical weathering. Okay, so what we're looking at here, actually we're going to skip this as well. I'll take it back. On an upcoming slide, which should be here pretty soon, I will let you know what I want you to know about the products of weathering. Here it is. Okay, so let's go ahead and write all these down. So what might I want you to know about the products of weathering? And specifically, we're talking about silicate minerals here that come from igneous melt, granite in particular, making up the continental crust. All right, so quartz does not alter. It does not alter chemically. It might become smaller and more rounded by physical processes, but it will never chemically weather into some other mineral. Feldspars and micas, remember muscovite and biotite mica, feldspars and micas will weather into clay minerals. Clay minerals are the most abundant and the most stable products of weathering on this planet. There's a lot of clay on this planet. That's why there's a lot of shale rock on this planet. And what do we mean by the most stable products of weathering? We mean that the clay minerals, once they become clay minerals, they're not going to chemically alter into anything else. They will stay clay minerals. Hornblende and augite, which are mafic igneous minerals, they could do one of two things. They could either oxidize into oxide minerals like hematite, or they will undergo hydrolysis and turn into clay minerals. And then olivine. Remember olivine? With the olive green color, and it's abundant in the mantle, and it crystallizes out of an igneous melt at the highest temperature, and is stable at high temperatures, but not so stable at low temperatures. Olivine is going to oxidize and turn into oxide minerals like hematite. We've seen this image before, but I'm showing it to you again. Just look at the one on the top left. This is what the clay minerals look like with a scanning electron microscope. So they are so small, you can't see them with a regular microscope, leave alone with the naked eye. And indeed, remember that they are sheet silicates. Okay, so physical and chemical weathering. So we discuss these as separate entities simply because we're trying to point out the differences between them and that there are specific types of physical weathering and specific types of chemical weathering. But just know this, they are not mutually exclusive. They work together as a team, okay? So most, really all the time, you're going to have both of these things going on in a system, both physical weathering and chemical weathering. Okay, I like to show this image in class, and hopefully we'll get to do that. My plan is that we will spend maybe a couple of weeks on this particular unit, and then 1 week on metamorphic rocks. So hopefully we'll get to show this image in class. And I'm going to ask you guys, what kind of weathering do we have here? Is it physical or is it chemical? Or do we have both? Do we see any signs of breakage here? Sure, look at all those clear glass bottles that are broken. That's physical weathering. Do we see any signs of chemical weathering? Well, yeah, look at those rusty cans. And what kind of chemical weathering is that? Well, oxidation, of course. Okay, so more on weathering. This first bullet here, well, the first and second bullets, I think both are important. All right, so the more exposed surface area you have, the faster the weathering. And we'll do a little demonstration of this in class using a cardboard box. So we can say that weathering is going to happen faster anywhere you have an exposed surface, like the top or the side of a rock. It's going to happen faster at edges, but fastest of all at corners where you have three surfaces meeting. But I want to point out that exposed surfaces doesn't just mean the top of the rock and the sides of the rock. Remember talking about joints, those fractures that go back into the rock? That is considered exposed surface area as well. So what this leads to is something we refer to as spheroidal weathering, which is where your rock might begin in the shape of, say, a square or a rectangle, and it becomes spheroidal. All right, we have three different scenarios here. On the left, we have one big square piece of sandstone. In the middle, you have cut that piece of sandstone into 8 smaller cubes. And then on the right, you were very expeditious and you have cut it into 64 cubes. So each of those 8 cubes you cut into 8 smaller cubes. Okay, so which of these groups of sandstone here is going to weather the fastest? Okay, it's got to be the one on the far right, correct? Because now you have greatly exposed the surface area. So just some examples here. So in class, I like to point to the image on the top left there. So the hiker there is stopped to take a break. Look at that big rock beside the hiker. Now it looks like an egg shape, but when that first weathered out of the bedrock there, it would have looked more like a rectangle. Okay, so spheroidal weathering has occurred here for sure. And spheroidal weathering can actually lead to rocks looking really quite round, kind of like a volleyball. Okay, so in class we will show this and we're going to discuss why. Why has one withstood the test of time and the other one is just, you can't hardly read it. Okay, so the one on the left is made of granite and was erected in 1868, while the monument on the right was put in place there in 1872. It's actually 4 years younger than the one on the left, but the one on the right is made of limestone. Well, it's made of marble, which is a calcite-rich metamorphic rock. It's basically recrystallized calcite or recrystallized limestone. Okay, so bottom line, the granite there is made of strong silicate minerals. The marble there is made of calcite. Calcite is much easier and fast to weather and erode. So you can't read about half of that on the tombstone to the right. Okay, weathering and soils. So we are going to discuss this in class, but for those of you that will not make it to class, there are basically 5 controls on soil formation. Number 1 is bedrock type, which can sometimes be referred to as parent material. And the geologist would say this is the most important control on soils. Of course, the climatologist would argue and say that climate is the most important. But anyway, so the bedrock type is important, and just to give you some examples, if you have shale as your bedrock and you're just going to produce a bunch of clay from that, that's not going to form a great soil. But if you have igneous rock, particularly extrusive igneous rock, that's going to form fertile soil. Second one there is climate, which is the most influential. And basically you're talking about average temperature throughout the year and precipitation. Time is number 3. Time is important. It takes time to form a good soil. Okay, number 4, I like to write this on the board as organic matter. Some textbooks might refer to it as plants and animals. If you don't have some organic matter, then it's not a soil at all. It's just simply sediments. And then the last one is slope. Slope is going to matter, and we'll discuss it more on the next slide. Okay, so look at this image here. You have three scenarios. On the left, you've got some rocky highlands, and they're showing you an image of the top of the Grand Canyon to compare. In the middle, you have a river valley, and they're showing you a cornfield. And then on the right, you have, well, just sort of undulating pasture land. All right, so which of these places is going to form the best soil, the thickest soil deposits? Well, your lowlands, of course. First of all, that area is flat. It's going to bring in sediments from either side. You also have that nice meandering river there that's going to deposit more sediment. So you're going to get your best, thickest soil there in the river valley, which might explain why did people ever settle on the Mississippi River to begin with. Well, it was transportation, but it was also great farmland. Of course, it also floods from time to time. And then over there on the rocky part on the left, you know, yeah, you have some rainfall and you have weathering and you have some living creatures. You might form little bits of soil here and there, but you're not going to get thick packages of soil because most of that soil that forms on the slope there is just going to get washed down into the valley. Okay, so a couple things here. I'm going to want you to write down the term regolith. Regolith is basically an engineering term that is just referring to, well, it's geology and engineering term, referring to rock and mineral fragments produced by weathering. And then down on that third bullet, I want you to know what humus is. Okay, so there's one M there, not two, so it's humus, not hummus. And humus is simply referring to organic material. Now we're going to look at that pie chart over there to the right. You see there that what's making up the biggest component is the mineral material. So the bedrock type does matter. Okay, so in your pore spaces, the open spaces in between grains, if you're below the water table, you'll have water. If you're above the water table, you'll have air. And how much organic material do you need? Not a whole lot, maybe only 5% for an idealized soil, but still you have to have some organics because if you don't, then it is not soil, it's just sediment. Here is the soil texture triangle. You do not need to know this for your exam. You have sand on the bottom left, silt on the bottom right, and clay at the top. So the soil scientists say that the best soil, most fertile soil is that stuff sort of bottom middle that's described as loam. So you have very little clay and it's about half sand and silt. And then there's all the other types of soils are listed there as well. You can pause here and look at it if you would like to. Soil horizons, this is not going to be on your exam. Once upon a time it was, but I took it off of there. So we'll just very quickly go through this. On the top you have the O horizon, which is where you have most of your organic material. Below that is the A horizon, mineral material with some humus. Together the O and A horizon make topsoil. Then you have the E horizon, zone of leaching, which means that you have water-soluble minerals get dissolved in groundwater and taken to lower levels. And then those minerals then accumulate there in the B horizon, zone of accumulation. Down at the bottom, you have your unweathered bedrock, parent material, and then in between the C horizon is kind of cool. It's where you're starting to weather that bedrock. So what's important to point out here is that weathering of rock doesn't just happen at the surface, it's also happening in the subsurface. Okay, and we see proof of that right here. So that bedrock is down at some depth, but it's still being weathered. Why? Because you have water and oxygen getting down to those depths to do the weathering. Here we are comparing a soil profile from South Dakota on the left to Puerto Rico on the right. And the one from South Dakota, you clearly see your topsoil. That's the part that's in brown and black. The A horizon portion of that is the brown. The O horizon portion of that is the black. And then it looks like you have a small layer maybe of the zone of leaching, and then the lighter colored stuff towards the bottom is your zone of accumulation. And then over there in Puerto Rico, that's pretty much all topsoil. Extra credit question here, potential extra credit question for your second exam. What is the state soil of North Carolina? Who knew we had a state soil? We do. It's red. It's called the Cecil soil. Why is it red? Because you actually have accreted island arcs making up the Piedmont of North Carolina, the central part of North Carolina. including some mafic material. So you have some iron and magnesium minerals in those mafic igneous rocks there. There's also felsic igneous rocks there. And all it requires is oxidation of the iron and magnesium, producing the red sisal soil. Okay, classifying sedimentary rocks. Just general things here, so you will want to write these three things down. Three general classes or groups of sedimentary rocks. We'll begin with what we refer to as clastic or detrital. Two words that mean the same thing. These are sedimentary rocks formed from pieces of pre-existing rock, as in mineral and rock fragments weathered out of bedrock. Then you have biochemical sedimentary rocks. Bio, of course, tells you that life is involved. So these are basically formed from the remains of once living organisms. It could be shellfish or it could be plants. And then you have chemical sedimentary rocks that form as minerals precipitate or grow out of water, be that groundwater or surface water. We're going to see some examples on the next slide. Examples of clastic detrital rocks: sandstone, siltstone, shale, also breccia and conglomerate. Examples of biochemical sedimentary rocks: limestones, any limestone, but fossiliferous limestone is the most fun, but also coal. Coal is a biochemical sedimentary rock formed from plants. And then for chemical sedimentary rocks, chert and travertine. But I'll tell you now that I will not ask you to know an example for the chemical sedimentary rock on your exam. This is a neat image here. We're looking at the Bonneville Salt Flats. So in the map there, you see that where that is. So this picture is taken west of the Great Salt Lake. The Great Salt Lake is the tiny remains of a once much larger Pleistocene glacial lake referred to as Lake Bonneville, ancient Lake Bonneville. So most of that water has evaporated. What hasn't is making up the Great Salt Lake. And what do you have left behind? You have these big salt flats here. So this is an example of chemical sedimentary rock. This, of course, is biochemical sedimentary rock. Look at that beach. Wow, could you walk barefoot on that beach? No, you're going to cut your feet. It's going to hurt. You got to wear some shoes, at least some flip-flops. Anyway, some beaches look like this, where you have more shell material than sand. And then the rock there in the inset is a type of limestone called coquina limestone, which has a lot of shell material in it and maybe some quartz sand. Here we're looking at the Great Chalk Cliffs of Dover. That is in England. You have buildings in the foreground there for scale. So what is a chalk made of? Well, it's a limestone, and it's made of these little tiny animals called coccoliths that make their shells out of calcium carbonate. Anyway, that's where chalk comes from. And what's cool about chalk is it is a deep marine igneous rock. Okay, so it's exposed at the surface now, but it formed in a deep ocean environment in the past. Here we're looking at some examples of chemical sedimentary rocks. So agate, which looks like a geode but filled in, petrified wood, and then chert. There's three varieties of chert there. Okay, so stalagmites and stalactites in a cave are examples of chemical sedimentary rocks. They're referred to as travertine. So examples here, top left, biochemical. You see fossils imprints in that rock. On the right, that's chemical sedimentary rocks. Those are chert arrowheads. And then on the bottom left is a sandstone. That's a big sandstone. There's a garbage can there for scale. That's in some camping and or picnic area. Okay, classifying sedimentary rocks will not be on your exam, so we're going to fly right through this. But we don't just put them into a specific category, either clastic, biochemical, or chemical. We don't just give them a name, or how do we give them a name? There's other things included, including what is the size of the grains? What is the shape of the grains? Are they angular or rounded? What is the sorting? Are they mostly the same grain size or different? And then what is the cement holding it all together? Okay, sorting. Here are some neat images on sorting. So in the bottom right, that is sand. Notice the ripple marks. And that is well sorted sand. Okay, on the left, that is very poorly sorted. That is glacial till. You have things there of all different sizes mixed together. Notice there's somebody's rock hammer in the photo. Why is the rock hammer there? For scale, of course. And in the top right is moderately sorted. Just some images here of shape. Angular clasts over on the left, rounded clasts in the bottom right, partially rounded on the top right. Another look at the shape of our grains. So there on the bottom, you have two pieces of quartz that you begin with that weather out of a granite. One has a high sphericity, one has a low sphericity. They both become rounded. Okay, but they'll have a different shape at the end, but they're both considered rounded. The images on the top, okay, why are they circles with smaller things inside? We're trying to show what it would look like to look at sediments through a microscope. So sorting isn't just something that you see on a larger scale. When you're looking at small enough sediments that you want to better look at them with a microscope, they can vary from very poorly sorted all the way down to very well sorted. So the one on the far right there, very well sorted, that would represent a beach sand, high porosity and permeability. Some fun examples of poorly sorted rocks here include conglomerate on the left with rounded pebbles and breccia on the right with angular pebbles. Some examples of well-sorted sedimentary rocks include sandstone, siltstone, and shale. Okay, steps in the formation of sedimentary rocks. This is something that we will do together in class, but we're also going to discuss it here for the people that can't come to class. Okay, so there are 4 steps in the formation of sedimentary rocks. It all begins with weathering. That is step number 1, which of course is the breakdown of bedrock, due to both physical and chemical weathering. Step number 2 is erosion, which is the removal or extraction of sediment from the bedrock. I often use those two terms together a lot, weathering and erosion, but they are not exactly the same thing. Weathering is breaking them down, changing them. Erosion is removing those pieces from the bedrock. Transportation, of course, occurs as the sediments are carried away from the source area, with rainwater making its way into streams and then down into larger rivers and perhaps all the way down to the oceans. We're going to draw these steps on the board in class. All right, so still in the steps of the formation of sedimentary rocks, speaking of transportation, step 3, I'm going to want you to know the agents of transportation. What is doing the work? Water is moving the majority of sediment on this planet, but ice can also move sediment in the form of glaciers. It happens slowly, but ice is very strong and powerful and can move sediment pieces that are very big. And then there's also wind transportation, and we refer to that as aeolian transport. And what size sediments can be picked up and moved around by wind? Large or small? You guessed it, only small sediments like silt, clay, maybe some very fine sand. By the way, sand from the Sahara Desert can be blown all the way out into the middle of the Atlantic Ocean, just so you know. Step number 4, deposition. This is when your sediments eventually stop moving around and they are deposited. So they will settle out of water, ice, or wind, whatever brought them there. We refer to that as settling out of suspension. Step number 5, which may or may not happen, there are some very old sediments on this planet that might be 65 million years old and still never became rock. A lot of sediments will become rock, and that step is known as lithification. It is the process by which unconsolidated sediments will lithify and become sedimentary rock. Lithification will involve 2 steps, which we will see on the next slide. Lithification involves compaction and cementation. Compaction is simply the burial of sediments. They're being squeezed together. So some of the water that was in the pore spaces, open spaces between grains, will get removed, not necessarily all of it. So the sediments have to be squeezed together, but to become a sedimentary rock, they also have to have some kind of natural cement. So natural cements that glue the grains together as minerals precipitate out of groundwater in between the grains. We talked about the natural cements already on a previous slide. Some drawings here to try to show that. Okay, so the top two sets of drawings are just trying to show that these either sand grains can become more compacted. That's what you see on the top, or in the middle, those clay particles that look like little sheet silicates, because they are, those can become squeezed together and then they all line up parallel, making shale kind of get deposited in layers and break in layers. And then across the bottom, I'm glad we have artists that can draw. Again, jobs for artists. We're trying to show a natural cement. So over on the left, you see your sand grains and the groundwater. Over on the right, the dark rind around the grains, that is, we're trying to show that there are now minerals growing out of that water and effectively gluing those sand grains together. Okay, sedimentary structures. This is a lot of fun, and this is something that we will do in class together. Again, I intend to spend 2 weeks on sedimentary rocks. It might even spill into the third week. So we'll spend less than a whole class period on metamorphic rocks. That's okay, they're not as important to us. So sedimentary structures, you're going to need to know these. Okay, so what is a sedimentary bed? Also known as bedding. A sedimentary bed is a single layer of sedimentary rock that has a distinct top and a distinct bottom. If you have more than one sedimentary bed together, you refer to that as strata. Sedimentary formation, I might want you to be able to give me an example of a sedimentary formation for your second exam. We will have a drawing to go along with sedimentary formation in class. So it is a sequence of strata that is distinctive, meaning it's not exactly like any other strata anywhere else in the world, and it is recognizable and has been studied and written about. And it can be traced over a regional distance, so for some distance but not worldwide. So no sedimentary formation can be traced worldwide. Only the iridium layer can be traced worldwide at 65 million years ago. Let's think about that. We'll talk about that again later. Anyway, I will want you to know an example of a sedimentary formation for your second exam, and a good one to remember is the Castle Hayne limestone, which is found in southeastern North Carolina. So here we are looking at bedding, layers of rock, and then bedding planes. What are bedding planes? We're going to get to that shortly. I'm going to have some drawings on the board for you guys. But you can definitely see some individual rock layers here in each of these examples. On the left, those are all the same rock type. It might look different because you have some weathering and staining, but it's all the same rock type. Over on the right, that of course you have some changes in rock type as evidenced by the color. This is a neat little drawing. Why would we show an offshore shallow marine body of water with sedimentary rock forming below the water? Why would we show that and then have a picture of the Grand Canyon there? Well, the answer is this. There are marine sedimentary rocks in the Grand Canyon. I know of at least a couple of limestones off the top of my head that are in the Grand Canyon, including the Kaibab limestone, which is the top of the canyon. So these days, the Grand Canyon is pretty far from any ocean, but just know that we had ocean water over that part of North America in the past, as evidenced by the limestones that we have in there. Okay, so here we're looking at a couple of different limestones. This is just one part of the Grand Canyon layers that they have drawn here, by the way. They've not included the entire Grand Canyon in that drawing down there on the bottom, but do know this. There are at least a couple of limestones in the Grand Canyon. Okay, some other examples of sedimentary formations other than just the Castle Hayne limestone, which is relatively local. Again, it's in southeastern North Carolina. The Kaibab limestone at the top of the Grand Canyon is a good example. The Coconino sandstone, which is a very famous sandstone in the Grand Canyon. I have some samples of Grand Canyon rocks that I will attempt to remember to bring to class with me, and I'll just stand there at the front and hold them up because we can't pass them around anymore. Okay, important exam question here, short answer question. Why does bedding occur? So sedimentary rocks are in layers. Why? Why do we have those layers? Why do we have sedimentary beds? And the answer is because sediments are deposited episodically, meaning in episodes or spurts, a little bit at a time, not a whole lot at a time, okay? So a good example is floodplain of a meandering river, and every time you have a flood event, you get a little bit of silt deposited on the floodplain, and eventually that can build into a siltstone of the future. But that's why you have bedding or layers, because sediments are deposited in episodes, spurts. Okay, sedimentary structures. This is something that we will draw in class, and everything that I draw in class, I will also then film from notes from the board and put on Canvas as a video lesson. Okay, so sedimentary structures. So we've already learned about sedimentary beds, which are just individual layers of rock. How about bedding planes? Bedding planes are simply the boundary between two successive or adjacent sedimentary beds. Then we have ripple marks. So ripple marks, well, they're ripples. They're small ridges, and they're going to form perpendicular to water flow. We have a couple different general types of ripple marks that I'm going to want you to know for your exam. Symmetrical ripples and asymmetrical ripples. Those are the shapes. What's important about the shapes is what it tells you about the water environment. Okay, so for the symmetrical ripples, meaning that if you cut a line down the center, they're going to look like the same shape on both sides, that's going to show that you have an oscillating current, as in tides. So we're talking shallow marine, beach area, tidal flats. These are also referred to as wave-formed ripples. So the ripples that are asymmetrical, meaning that if you cut a line down the center, they are not the same shape on either side, are also referred to as current ripples, meaning they'll show you the direction of current. So current flow in one direction only. What kind of water flows in one direction only? Rivers and streams. So ripple marks that we find preserved in the rock record, and the water is long gone, looking at the shape of the ripple marks, we can tell what kind of water environment it was. So in the image on the top left there, that is a tidal flat, and you see ripple marks there. So even though you can't really tell from the angle of this photograph, they're going to be symmetrical. There's a quarter there for scale. Look at the image down there on the bottom right. That's similar to what I'm going to put on the board. So the image on the top, notice that those are symmetrical ripples, and the image on the bottom, those are asymmetric ripples. What's important about that is what kind of water environment put those ripple marks there. So that's what you're going to need to know for your exam. You're going to have drawings of the two different types of ripple marks. I'm going to ask you what kind of, to match it up, what kind of water environment do we have there in A? We have symmetric ripples. It must be some kind of marine environment, salt water. B, when we have asymmetric ripples, well, that's a river or stream. Here is a really neat image of ripple marks preserved in the rock record. Somewhere, I don't know where this photo was taken. This comes from a textbook we don't use anymore. And I kind of wish, we could get a better idea of whether or not they're symmetrical or asymmetrical. It's hard to tell from the angle that they've taken this. But sometimes there's other things that can tell you. For example, if you find any trilobite fossils in there, or what they call Cruziana, tracks of trilobites, then that would tell you they were marine, because trilobites were marine arthropods that lived all through the Paleozoic but are extinct now. Moving on with sedimentary structures. Dunes. Okay, so what are dunes? Well, dunes are ridges like ripple marks, but they're bigger. They could be tens of centimeters in height to meters in height. And they're going to form either in arid regions like deserts or on coastlines. So, okay, crossbedding is next. So what is crossbedding? Crossbedding, some sandstones will have crossbedding. I'm going to show you an image on an upcoming slide of what crossbedding looks like. I will attempt to draw this on the board. So crossbedding forms when you have your dunes. They can also occur in ripples. Migrate due to either wind or water. Okay, so I will ask you a question on the exam. What do large cross-bedded sandstones represent in the rock record? If they are large, dune size, and they are cross-bedded, that tells you you're looking at an ancient desert. And the wind was blowing the sand around, which produced the cross-bedding. So this is kind of neat, okay? So on the bottom right, you have dunes near a coastline. And then on the top left, you have cross-bedded sandstone. So it's kind of a before and after image. Millions of years in between here. So that image in the top left, that is from, I believe, Zion National Park. I can't remember if that's in Utah or Arizona. But this area is either part of Zion National Park or close to it. It's an area known as the Wave, and you got to hike in to get to it. And it's great for hiking or mountain biking. Anyway, it's a very beautiful place. I've never been there in person, but I like to look at pictures of it. Anyway, what you're going to notice there, those rock layers, they're not just flat lying and all parallel. Some of them are at angles to each other. That is cross bedding. So these cross-bedded sandstones here, like you find in Zion National Park, tell you that it was a big desert in the past. Okay, graded beds. Graded beds mean that you have these packages or layers of sediment that are stratified or layered according to grain size, meaning you've got larger grains on the bottom and then they get smaller as you move on up. And graded beds tend to form in a particular environment we refer to as a turbidite flow, underwater landslides. Mud cracks. So mud cracks, you'll see some images on upcoming slides. If you come to class, we'll look at some of these from Google Images together. So mud cracks are basically just cracks in the mud. They could form either in arid environments, desert environments, or they could form on the tidal flats during low tide on hot days. And fossils. Fossils, of course, evidence of past life. Fossils are themselves sedimentary structures. If you want to learn more about fossils, then you would want to take Earth history in the spring. Okay, so what do we see here? Top left there, you see graded beds. You've got your more coarse material on the bottom, and then the grain size is going to increase to the top. And that represents an underwater landslide in that location in the past, meaning that that was offshore in a marine environment in the past. Over on the right, those are mud cracks in the rock record. And then in the bottom left, does anybody know what that creature is called? If you said trilobite, you're correct. It does kind of look like a horseshoe crab, but it's not. That's a trilobite, extinct marine arthropod. Coal. Okay, what am I going to want you to know about coal? Well, the first and third bullets here, you're going to need to know for your exam. So coal. Coal forms in warm, swampy environments. Coal is a biochemical sedimentary rock that forms from accumulated dead plant material in a swamp. Now, most of the coal that we mine today, well, most Appalachian coal, formed during the Carboniferous period, Mississippian and Pennsylvanian, roughly 354 to 290 million years ago. So during a relatively short period of Earth history. But coal forms in warm, swampy environments from plant material. Why does that happen? This is why that happens. You don't have to know this part for your exam, though. So swamps, they have poor drainage. And everybody knows that swamp water is stagnant and it doesn't smell that great, and you don't really have any current or flow to it. So you're not getting dissolved oxygen in there. So we say that swamp water is anoxic, meaning very little oxygen. Therefore, there are very few organisms that can live in that anoxic water to decompose organic matter. Therefore, when plants die and their remains litter the base of the swamp, they're just going to accumulate over time. And you get all this plant material to just kind of squeeze together and eventually form coal, which is high in carbon content. You will need to know this first bullet here. Okay, for every 10-foot coal seam that you might see today in the mountains of Virginia, West Virginia, Kentucky, it took 100 feet of peat to form it. So peat is the name we give for that dead accumulating plant material that we find in the swamps. So just know that. You've got to squeeze it down to 1/10 of its original thickness. Very concentrated carbon. So 100 feet of peat for every 10-foot coal seam. Okay, so coal from West Virginia is very high in sulfur, and they tend to keep running these very old power plants that are exempt from the Clean Air Act, so you release a lot of sulfur into the air, and that's not good because it can mix with rain and make acid rain, sulfuric acid. And then coal, there's a lot of issues with coal. By the way, coal is not really in demand anymore. And that's not the fault of any particular people or any political party. There's just not so much demand for coal anymore. It's just how it is. Get over it. Anyway, coal used to be mined exclusively underground, but unfortunately there's a lot of surface mining now. And the worst type of surface mining ever is called mountaintop removal valley fill. So we'll get to that mountaintop removal valley fill shortly. Exam question here in the form of, I want to say matching, putting it in the correct order. The coal sequence. I'm going to want you to know the coal sequence from what we begin with to the highest grade of coal. So it all starts with peat, dead accumulating plant material. So you squeeze that down over millions of years and you get something we refer to as lignite, or soft brown coal, which is the lowest grade of coal. You squeeze that together some more and you get bituminous coal, which is a higher grade of coal. That's what we have in West Virginia. And then if that bituminous coal is caught up in a mountain building event and metamorphoses, then you get anthracite coal, which is a very high grade of coal, and it is metamorphosed bituminous coal. And you find some of that in Pennsylvania and some parts of New England. So peat is just sediments. Lignite and bituminous coal are both sedimentary rocks, biochemical in nature, and anthracite coal is a metamorphic rock. Anthracite coal is the highest grade of coal, and we have very little of it. Okay, so this is a nice image here, I think from a textbook we don't use anymore, showing the different steps. So on the top, peat, just material accumulating in a swamp. There's a picture of what peat would look like. You see what looks like part of a stick in there. Okay, and then the second image down, lignite. So you are starting to bury and compact all this plant material. Notice the top of the ground there on that second drawing. It's not a swamp anymore, it's a grassland. A lot of time has passed. So as you continue to put more sediments on top and you squeeze that material down to a lesser thickness, you concentrate it even more, then you get your bituminous coal. And then notice that image on the bottom. Well, first of all, the rock layers there are no longer horizontal, flat lying. Now they are undulating. We have created anticlines and synclines. And then the pink arrows there are showing squeezing on either end. Okay, so at that point, that bituminous coal, they got caught up in this mountain building event. It metamorphoses into anthracite. Here we are looking at coal seams. Okay, so on the left, I'd say each of those coal seams is at least 20 feet thick. So think about all the peat it took to form that. On the bottom right, that is an image from mountaintop removal valley fill coal mining in West Virginia. It is the worst thing ever to happen. Well, it's one of the worst things to happen in West Virginia, in my opinion. Anyway, it's terrible. So you have this pristine mountain, and you have woods, and you have animals living there, and you have people living in the valleys below. And the coal company comes in and they blast off the top of the mountain with dynamite to get to the coal. And then they push the overburden down into the valleys, down into the river valleys. And they ruin these streams. and they release a lot of toxins that get into the well water of people, and it can cause cancer and other issues. So always at the end of the semester, I show a documentary for extra credit called The Last Mountain, and that's what the documentary is about. Well, with COVID, what I'm going to do is just, when it comes to the end of the semester, I'll give you guys the link where you can watch that video on YouTube, and then you will write a 2-page double-spaced essay about it and email that to me to get your 10 points on one exam. Coal fields of the United States. Okay, so your lignite is in the sort of grayish color. Now they're going to cut bituminous up into bituminous and subbituminous. So coal out west is more of subbituminous, and lignite a little bit of bituminous. Notice there's a lot of bituminous coal in the Appalachian Mountains, but also there in the nearby Midwest. Anthracite, you got some in Virginia there, and Pennsylvania, and up in New England. And then you have Alaska there with some bituminous and subbituminous coal. How come Hawaii is not on this map? It is the United States, but they don't have any coal. Good for them. That means nobody's over there digging it up and poisoning everybody. So if there's time, we'll look at this pie chart in class, and this goes way back to 2001. Wow, that's like, nearly 20 years ago. Has this pie chart changed? Yes, sure it has. Okay, so what's a part of this pie chart that may have gotten smaller? The coal has definitely gotten smaller. What's a part of this pie chart that has gotten bigger? Natural gas has gotten bigger. What's a part of this pie chart that we hope has gotten bigger, and probably has, and that would be the renewable energy. So here are some nice drawings just showing, reminding us that sedimentary rocks are important for resources. So on the top left there's an anticline with a shale cap, and you've got your oil trapped in the pore spaces on top of the groundwater. That's where we would go and drill for oil. Top middle is just reminding us that limestones, by the way, the brick pattern there is limestone. Limestones make a good aquifer, as do sandstones. Coal, of course, on the image on the top right. Bottom left, we quarry limestone because we need it to make cement. Bottom middle, underground salt mines. And then the bottom right, the uranium is originally coming from the granite down below, but it can migrate up into the sandstone, and we will likely go and get it there. Transgression versus regression. We're finally getting to the end of this unit. Okay, that's good because this one is long and it's going to take a long time for this to upload to YouTube. Transgression versus regression. You need to know this for your second exam. A marine transgression is a sea level rise, as in the sea is transgressing upon the land. When does this happen? When we have a warming climate. A marine regression is the opposite, when the sea level falls back, and that's only going to occur during periods of glaciation or ice ages. How do we recognize this from the geologic past, looking at the rock record? So, marine transgression in the rock record, I'm going to draw this for you in class. So, let's say we have a sequence of strata, or a stratigraphy column, a series of rock that we've drilled out from the subsurface that has conglomerate on the bottom, which is a land-based rock, sandstone above, and then limestone on top. Your limestone is the marine rock. In a sequence of rock, if the marine rock is on top, that shows you it was a transgression. So this drawing here is showing that, or this strat column in the bottom left there. So you have your limestone, your marine rock on top. That shows you a marine transgression in the past. And then the images on the right, time 1, time 2, and time 3, are showing you how this sequence of rocks was slowly deposited. And in this image here, they're not giving us anything for scale, but what we're trying to show is that we can map out these transgressions and regressions over many, many dozens of miles. Okay, so we might go from, say, the Wilmington area on the far right up to getting close to Raleigh on the far left. So the blue brick pattern is your limestone marine rock. The green dashed line area is shale. That could be a marine shale or a floodplain shale on rivers. Then you have a sandstone on top of that. Those could be sandbars in rivers in the continental area. And then over on the far left, the round circles, that's showing us a conglomerate or land-based rock. So here, if you look over on the far right, you see that the limestone is encroaching up onto those continental rocks. That's a transgression. How about a marine regression in the rock record? Would look kind of the opposite. Okay, so if you have your limestone on the bottom, your marine rock on the bottom, and then a sandstone above that, and a river shale above that, that's a marine regression in the rock record. So here is something similar but opposite of what we looked at before. In this case, the limestone's on the bottom, covered by terrestrial sediments on top. Maybe a tidal mudstone, but then a beach sandstone on top. And the images on the right are showing you that with time, this time, the sea level fell back. So that's a regression in the rock record. Just as we can map a transgression over a longer distance, we can map a regression over a longer distance as well. And this, I want to say this is our last topic, but it's not, because we'll do a quick thing on mass movement, landslides. Sea level rise. I want you to, guys, I'm going to want you to know the difference between eustatic sea level rise versus local sea level rise. Eustatic sea level rise is global sea level rise. I mean, it's happening all around the planet due to natural and or anthropogenic global climate change. So sea level rise has happened plenty in the past due to Milankovitch cycles, but sea level rise is happening currently very quickly due to global climate change induced by humans. So eustatic sea level rise is referring something that's happening all across the world. Local sea level rise, though, is different, and it's referring to particular localities. So local sea level rise may be different from eustatic due to either tectonic uplift or subsidence. We'll talk more about that on an upcoming slide. All right, so some examples here. If sea level rise is predicted to be approximately 1 foot over the next century, different locations may experience greater or lesser degrees of sea level rise. That's an old number, by the way. Now they're saying it could be anywhere from 1 to 6 feet. Hopefully it won't be the worst case scenario, but we don't know yet. Anyway, not everywhere will experience sea level rise the same as everybody else. Okay, so if it is going to be 1 foot over the next century, then here on the East Coast, that's pretty much what we're going to expect. 1 foot of sea level rise over the next century, which will inundate the land a lot more than any 1 foot when you have a nice, gentle continental shelf like we do here on the East Coast. But we're going to compare New Orleans to the Pacific Northwest. New Orleans will have greater local sea level rise than eustatic because New Orleans is also sinking. Okay, so we have put a lot of dams and levees and flood control features on the Mississippi River to prevent flooding and loss of life, but now the New Orleans, the wetlands there, that area is sediment starved, so it is sinking as sea level is rising. Also, the oil and gas companies keep cutting new channels through the wetlands instead of taking old channels, so they are also helping to destroy the wetlands and increase the subsidence. The Pacific Northwest may have a little bit less local sea level rise than eustatic due to tectonic uplift. So the type of plate boundary there is actually pushing the North American plate upwards. So the Pacific Northwest, Northern California, Oregon, Washington will experience less sea level rise than New Orleans or the East Coast because the land is uplifting. But there are other prices to be paid, such as earthquakes and active volcanoes. All right, so here's an image of, on the top left, those are Louisiana salt marshes meant to protect the coastal areas and be a sink for pollutants and be the birthplace for a lot of seafood. And then in the bottom right, that is what part of New Orleans looked like when after Hurricane Katrina. Exactly. Pacific Northwest, different story. Okay, look at that coastal image there on the left. Looks a little bit different from the Outer Banks or Wrightsville Beach, doesn't it? Yes. That's because the West Coast is an active margin while the East Coast is a passive margin. So you can sometimes have some short sandy beaches. And you do have some sandy beaches in Southern California. That's a different plate boundary there. Anyway, so this area, Pacific Northwest, is experiencing tectonic uplift and will not have quite as much sea level rise as the rest of the world. So you see there in the map, you see those mountain ranges. Okay, that's the Cascades there. And then some of those mountains are shown with a maroon triangle. What is that triangle representing? Active volcanoes. So there are several active volcanoes there because of the plate boundary that is there pushing the land up. We'll learn more about that later in the semester. Okay, mass wasting. This is now officially the last topic. Maybe we can have this presentation be no more than an hour and 45 minutes. It's going to take forever to download to YouTube. Oh well. Okay, so mass wasting, what is it? It is the downslope, downhill movement of rock, regolith, soil, and everything else under the direct influence of gravity. What is the controlling force here? Gravity. Now we're going to talk about some triggers of landslide events. So, having steep slopes, of course, is setting you up for mass wasting. Gravity is the controlling force, but there are certain things that affect the timing of when it happens. Mass wasting triggers. So if you have too much rain, as in saturating that material with water, that can make that material flow. So what we're looking at here on the bottom, 3 different scenarios. You're on the beach and you got a bunch of dry sand and you're trying to build a castle, but the grains won't stick together. They're only going to be in this cone kind of shape, and it can only get to be so steep, otherwise the particles will run downhill. If you add a little tiny bit of water and the sand is damp, then you have some cohesion among the grains, and then you can build your sand castle. But if you just pour buckets of water on that sand and really saturate it, or rather if you put a bucket of water on your sand castle, guess what? Now it's just going to flow. You're not going to have a sand castle anymore. Because if you saturate in between the grains there, it's going to reduce friction and you're going to have flow occur. What else is a mass wasting trigger? Over-steepening of slopes. So every unconsolidated material has an angle of repose, which means what is the greatest natural angle that that material will stay at an angle and not all just collapse. So anything that humans do to oversteepen a slope, like go in and build roads into the side of mountains or build housing developments into the side of mountains in California, oversteepening the slopes, that's bad, and that can set up the conditions for mass wasting. Other things, removal of anchoring vegetation. This can either be humans going in and clear cutting the land, or it can be fire. The fire can be naturally started. The fires in California right now, they're saying they were started by lightning strikes. They had 100 lightning strikes. Lightning strikes don't always cause catastrophic fires, but if the place is experiencing drought and not having rain in a while and is very dry, then it's more likely to happen. So either humans or fire removing vegetation can help lead to landslides, because when the vegetation is alive and healthy, the roots down the subsurface help to hold the hillside together. But when that vegetation dies, then the roots start to die as well, and then that material can flow. And of course, earthquakes can trigger mass wasting as well. Now, there are different types of mass wasting, but that's not going to be on your exam. So you can go through these slides on the different types if you want to, but they will not be on your exam. Slumps are kind of neat. You got a little rotation. Rock slides are very scary, especially when they land on the roadway. You hope no cars are there, no people. Debris flow debris slides. There are actually many different types of mass wasting, but you will not need to know the types of mass wasting for your exam. Creep's kind of neat though because it's a very slow movement. Might cause fences and utility poles to tilt. That is it. Yay.